Okay, gang, let's begin. We're going to talk about reflection and refraction. But first of all, let's play a little game. And a little game be called Fermat's Principle of Least Time. It's kind of covered in the book, so I want to go over it kind of quickly. If we played a little game where you want light to go from A to B in the shortest time, what would the path be? Straight. Wouldn't it be a straight line? Yep. But let's suppose we made an added provision that it's got to touch a line down below on the way. Now it's got to go from A, touch the line, and back to B. What would the path be for the shortest time? Turns out to be shortest distance. Would it be like this? Would it be like this? Are there shorter paths? Answer begin with a Y. Yep. Okay. How about right exactly in the middle? No. How about it? Right exactly in the middle, bend like this? Would that be the path of shortest time? It turns out the answer begin with an N. No. And it turns out there's a nice technique for finding it. Let me go through it quickly. If you consider this, whip, boom, fold it down. Okay? Fold it right down so it's over here. And call it B prime. I could ask you guys, what's the shortest path between here and here? And you would all say what? A straight line. In fact, you just go like this. You say, that's the shortest path between those two. What's the shortest path between here and here? Touch this line. How many see it already? Well, this line here, folded up like that. The distance here is the same as the distance here. Yeah? So it turns out what the light will do, the light will hit here and then go up to here. See? Like if you put your eye here and you look down in the mirror to see this, you will look right there to see it, not right here. Okay? Now I've got an exercise for you. What I've done is I've shown where the image of B would be down here. Huh? What would be the path of least time to go from B to A? Can you, at your seats, fold A down and do it? Go. Do you know what I'm saying? I don't know what to do. Come on, you know what I'm saying? I'm saying do it all over again. And this time, we want to go from here to here, but we want to know where to go to touch the mirror. The only reason I'm having you do this is because if you do it, then you'll be learning. If I do it twice, you'll see me do it twice, and you'll be convinced I know how to do it. I want you to know how to do it. Go. Let's see who's the last one to finish. What you do is this. You take A and fold that down. Whip, boom. Call that A prime. Now if I ask you what's the shortest path between here and here, no contest, huh? You guys would just say this. But I didn't. No, but how about the shortest path between here and here, and you got to touch here? Bam, there it is. Because this distance, same. And let me tell you what this all turns out to give, gang. This angle and this angle, guess what? Will always be the same. Okay? So light going from here to here, ba-boom. Or coming back from here to here, ba-boom. You're at the restaurant. You're at the restaurant and you're eating there all by yourself as usual, and you look on the mirrored wall and you look over and, oh, there she is. Miss Wright. You can see the mirror image of Miss Wright. So then you start to kind of fix yourself up a little bit because you're wondering, if you can see her, can she see you? And what's the answer? Yes. Check your neighbor. If I hold this mirror in such a way that I can see you, can I be assured that you can see me in the mirror? What's the answer? Begin with a Y. End with a P. Yep, that's true, yeah. Principle of reciprocity, okay? From here to here, from here to here, same. The path would be no different if you change direction, okay? So the law of reflection, gang, is simply that the angle of incidence, light coming in, hitting a mirrored surface, will be equal to the angle of reflection. It's common to measure those from a vertical line perpendicular to the surface called the normal. So we usually say this angle, same. Everyone that plays pool knows that. When you're playing pool, when you bank your shots, you know that the angle you come in, the angle you come out is the same. Any question on that? Now this holds for not only plane mirrors, but all kinds of mirrors, even curved mirrors. Because at any face, the light coming in, boom, will bounce off at the same angle. This angle will always be the same. And that's even true of what's called diffuse reflection. If you look at a surface that's very, very rough, okay, light coming in will hit right here. And see this angle here? It'll bounce off like that. Maybe light coming right over here will hit there and maybe bounce like that. Maybe light hitting, maybe like right in between here will hit a face like that and bounce off like that. It'll go in kind of all directions. Some will even bounce right back to the origin if the surface is rough. And it turns out the paper that your books are made of is rough or smooth. That's a relative question. But it's rough compared to the wavelength of light. So for a light wave, this is a very, very rough surface. And ain't that nice? Because light coming down will bounce off in all directions, and you can hold your head anywhere and see the book. See, if the book were a mirror surface, you could only see it in certain places. Isn't that neat? This happens at nighttime when you're driving. Ever be driving at nighttime when it's raining out? And it's very difficult to see the road ahead. Do you know why that's true? If the road is dry, the surface is rough. And your headlights will come down, and some of that light will come back to you. And you, the driver, have enough light coming back through your windshield to see the road ahead. It's illuminated by your headlights. But what happens on a rainy night? Is the surface rough? The surface, honey, is mirrored. Now it's like a mirror surface. Your headlights come down, boom, bounce off. Ahead. Nothing coming back to you, hardly. So you say, hey, if I get the lights on, you can't be sure you even have the lights on. Because you're going from a diffuse reflector, the surface, rough, to a mirrored reflector, the surface with that layer of water. You've all noticed that. And that makes it even extra dangerous because that light that's coming down, ordinarily some of which come back to you, now, boom, all goes ahead to whom? To the other driver coming at you. And so the other driver has what? Glare. So that's why rainy nights, poor visibility for those reasons, huh? Kind of interesting, yeah? Consider a candle. All optics books consider candles for objects, okay? Now we're going to look at the image that this candle gives in a mirror. Let's suppose right here we have a mirror surface. Now what happens is light, let's just take from this point. Light goes in all directions. Some comes straight ahead, some comes up like this, some comes like this. The light hits the mirror in all directions. And when it hits the mirror, it, boom, reflects, yeah? And it reflects how? There's a normal, a normal, normal, normal. It reflects such that this angle, for example, here, will be equal to this angle here and reflect like that. And up here, this will reflect right back to where it came, yeah? Because it hits flush, huh? Right angle, huh? Up here, like that. And up here, like that. And down here, like that. Where this and this are the same. I don't have that drawn very well, yeah? Like, maybe like that. Get the idea? Now, you have your eye out here and you're looking. These rays here are all diverging. They're spreading out, see? They're spreading out this way, just as if they were this way, see? It's like this continued, huh? But that spread out looks to you like that ray came from back here, that ray came from back here, that ray came from back here, that ray came from back here. It looks to you out here like there's a flame here and also a flame back here. And I could draw the same rays for the bottom of the candle. That's done in your book a little bit, yeah? Okay? And the bottom of the candle, it would look to you like it's over there. And so you would see the candle here, and you would see the image of the candle. And let me ask you a question. What's the distance here, here, and the distance here, here? Begin with SS. Check your neighbor. Same, gang. Same. So if you're taking a photograph of you and your friends standing in front of a mirror, all right? And you don't have a focus, the device you can look through, but you have a setting. And let's suppose you're like you're 3 meters in front of the mirror. You're taking you and the gang, yeah? Now you want to set your setting for 3 meters or what for your image? Check your neighbor. Okay, gang, what would be the answer? You stand 3 meters in front of the mirror, what are you going to set your setting for the image? Where? How many meters? How many say answer begins with a... How many say answer begins with a... Yeah, it's 6 meters. Your image is going to be 6 meters away. So your image will be as far behind the mirror as you are in front. Make sense? Yeah. Now if you have a curved mirror, different rules, okay? And it turns your image distance will be more complex. We won't cover such thing now. You know why? Because it's a little bit more complex, and we want to get the easy stuff down cold. Reflection is one thing. Refraction is another. In this case, the light hits the mirror and bounces off and stays in the air. Or it could be underwater. There's no change of medium. What happens when the light changes from one medium to another? What happens to the speed, gang? When light goes into a piece of glass, what's it do? Slows down. When light goes into water, what's it do? Slow down. When light goes from the vacuum of the space to the atmosphere, what's it do? Begin with SD. Slow down. You get the idea. It's slow, and we know why it slows, right? Because the light is interacting with the particles, right? And that interaction involves a little time. We're into that, right? And different colors interact differently, different colors travel different speeds. We get all that sort of thing, right? Let's investigate that a little bit. In fact, let's talk about the example that Richard Feynman talks about when he talks about refraction. It's a dandy. It's in your text. Let's suppose you're a lifeguard right here. And this is a top view of the beach. And here's a sandy beach. There's sand and water down here. This is a helicopter view. And down here is a person drowning. Drowning in the water because a shark's coming or something like that. Now you're the lifeguard type up here. And you want to get from here to here in the least time, okay? So you might say, well, I'll take a straight line path. Good idea or not good idea? Begin with NG. Not good idea, HC. Oh, you don't be knowing. Well, let me ask you a question. How fast can you go across the sand compared to how fast can you swim?
Faster.
How can you move faster, across the sand or swimming? How many people say, honey, I'm not so good in the land, but man, you should see me in the water. Come on, come on. Most of us can go faster across the land, yeah? So it might be that you would say, hey, what I'll do is I want to go the shortest distance through the water. So I'll run over here and then run straight down. Do you think that's the shortest time? Now, if you run very, very, very fast and swim very, very, very slow, case to be made, you approach that. But let's suppose you run fairly fast, and you can swim fairly fast, but not so fast. Would it be that, this, or something in between? Begin with IB. All right, begin with NB. All together, what is it? NB. It turns out your path going to be something like this. See? Okay, it's going to kind of bend like that, okay? And guess what behaves the same way? Begin with an L. Light. Light does the same thing. We call that refraction. To go from one point to another in the least time, and to do that by taking a bend. I can kind of show you that with this little demonstration. Inclined plane. And I get some wheels. And I'm just going to roll the wheels down the inclined plane. All right? What I'm going to do is I'm going to roll the wheels from a nice, smooth sidewalk onto a rough piece of material. It's almost like wheels rolling along a sidewalk into the grass, or light coming down and interacting with the material and slowing down. Did you see it bend? It came down like this and then bent. Let me put that on the board. My wheels are coming down in this direction. And they're coming from the smooth surface to the rough surface. When the wheels get to the rough surface, what happens to the speed of the wheels? Slow down. You know why they slow down? Because there's an interaction with the wheel and the material. Let's suppose it's like the little pieces of cloth on the towel, or maybe it's like blades of grass on a lawn, okay? There'd be some interaction, so this part would slow down. But what happens to this part over here? It continues going quickly. So what happens, it sort of kilters. And so what happens is it goes like this. When both wheels get in there, they're going the same speed, and they continue at a straight line. So there's no mystery as to why the wheels will kind of bend over, is there? I mean, if you move along like that and something's on the way, won't your arm go like this? I mean, part of it slows. Well, guess what behaves the same way? Light waves. When waves of light come from above, let's say hit water. Maybe the waves of light are coming from the sun. Something like that. And we got a ray coming down like that. Incidentally, it turns out a light ray and the wave fronts that represents, these are like the crests of waves. Think of water waves, yeah? Right angle in here, gang. Always a right angle. See, even the axis of a wheel and the direction in which it's traveling, right angle. See? So what happens over here? These waves of light come down. And when they hit the water, what happened to the speed of the waves? Oh, you don't know that. Well, check your neighbor. Oh, they somehow go faster. What's the answer, gang? They slow down, okay? The waves slow down, so what happens? They bend. And they sort of bend like this. And they get closer together. So the wavelength gets a little less in here. But the frequency of the wave stays the same. Does the frequency of a light wave change when it reflects from a surface, as we talked about before? What evidence do you have that the frequency of light does not change upon reflection? Do you have any evidence of that? What evidence do you have that the frequency won't change? Check your neighbor. How many people say, well, there's really no evidence of that, it's just in the textbooks and we believe it? Try it, gang. Hint, shall I pass this mirror around? If I pass this little mirror around, what would you do with the mirror to find out? You look at the color of your shirt, and you look at the color. Hey, son of a gun! Hey, the shirt got the same color in the mirror. Wow, the ceiling got the same color. Everything in the, hey, the same. What's that mean? It means there's no change in frequency. Yay. So if you got a blue shirt and you're standing in front of a mirror, gang, what's your image color? Begin with a BL. What if you got a red shirt? What would the image color be? Red. Yeah. So we see that, okay? It turns out going through a material too, the frequency stays the same, so the color stays the same. Even though the wavelength gets squashed up a little bit, yeah? So that's refraction. I'll show you an example of that. Root beer. Root beer is served in thick mugs. Why? Why thick mugs? Because they can give you less root beer for the same money, right? Let me test this to make sure it's really root beer. It tastes like Pepsi to me. Oh, by golly, it is Pepsi, all right? Now, you guys be seeing something? The root beer goes right out to the edge. Make it look like you got a lot of root beer in there. You got a lot or a little? Answer begin with a L. Turned out a little, because you got a lot of glass. But to the viewer, you see the right out to the edge. I wonder if there's a reason for that. How many people say, well, no, there's probably no reason for that. It's kind of just the way it is. HC gang. Let's look at a top view of that on the board. Okay. Here's our root beer. Okay. Let's look at a point right here. Light is going in all directions from there, huh? Now it bends when it gets outside, so let me just put in here. Light's traveling in all directions. And some of that light is coming like this, and some of that light's coming like that. And the light that's coming like this, when it comes through, what's it do? Does it keep going straight? No. How many say that when the light comes out from the glass to the air, it will speed up? How many can't say anything? They kind of just wait and they take notes. Do you see it's going to speed up, gang? Okay? It's like the opposite of this. When these wheels roll from here out, this wheel gets out first, it starts going faster, so it just unbends. Okay? So what happens, this light over here, the waves of light, okay, will now kind of come like this, bend like that. See what I mean? And over here, a place over here, rays of light come in all directions, maybe light coming like that, bends like this. A person's eye is right here. A person's eye looks out and sees root beer all along the edge. It's an illusion. The root beer is really in here. If the light didn't change speed going from here to here, then you would see the thickness of the glass. And I saw a very, very neat thing one time. I saw a bottle of Coca-Cola. And the bottle of Coca-Cola was embedded in a piece of plastic. So it turns out that the light wouldn't change speed very much going from the glass to the plastic. And when you look at that, you can see the Coke like this. And you can get a better representation of the true volume of the Coke. You know what I'm saying? You know what I'm saying? Okay? But when you take this out on the air, boom, there's a big change of speed, a big bend, and that bend makes it look like it's filling up more room than it really is. An example of refraction. Any questions?
Could you get the same effect if you put in water?
Let's try that. Let's try that. Let's try that. That's a good idea. Excellent idea. I never even thought of that. See the Ted right after class, will you? Let's try that. You kind of can. Can you kind of? Well, it's hard for you guys to see. It turns out I've got the water a little bit chalked up because I want to show you something else. But yes, you do get that effect. Excellent, excellent, excellent question. How come I never thought of that before? That's one thing about teaching. You continually get new ideas by people like you. And sometimes the simplest questions give the. Isn't that nice? See? Do you guys know why you can kind of see the glass now and you couldn't before? How about that for a homework question? Would that be a good one? We'll think about that. Let me show you something else with that. Here I've got a laser gang. Laser's emitting a nice, clear, single frequency red light. See the red light gang? See? Laser light, okay? It makes a nice, nice, thin beam. You guys can't see the beam right now because it's not scattering off anything. If I darken the room and put a little chalk dust here, you would see the beam shine and scatter. You know when you see a searchlight beam going up from a department store that's opening or something like that, you see the beam only if there's a lot of gunk or something in the air. If the air were really, really clean, honey, you'd see no beam at all. So you need something for the beam to scatter off. And what we have in here is some dairy creamer, a little dairy creamer and some water. So there's a scattering thing here. Can you see the light beam? What I'm going to do, gang, is put a mirror on the bottom here. And I'm going to see if you can see the light refracting. Lights, please.
Wow.
Can you be seeing such thing? Okay. Now, what I should have is a. Does anyone have any? Does anyone smoke here? No. Someone with a smoker, please come out and blow some smoke in here. It's for a B. Light up, James. Light up. Yeah, just blow it right in here, and then maybe we can see the beam that's off to either side. How come you smoke, James? You know about that? Blow a lot of it in there, James. Get over here. Right over here.
Careful of your eyes, though.
Can you guys be seeing?
Watch your eyes.
Oh yeah, don't get it in your eye, honey. That's lawsuits and all that. Look at it, never mind your eye. I'm thinking about the lawsuits. So you can get some over here too, James. Okay, what I want you guys to see is it coming down. You see the bending at the surface too. Can you kind of see that? Ain't that neat? Okay. Is that dramatic enough that you're glad you came today? Okay, thank you, James. Lights again, please. Okay, what we attempted to show there, gang. Yeah, dump it in the tank. Yeah. James, after class, I want to talk to you about smoking, okay? Hey, that's true. I heard that the nicotine is tougher to kick than heroin. Wow. Here's what we wanted to show, gang. And that most smokers begin while they're teenagers. Very, very few people get to the age of 20 and then take up smoking. It's all done at an earlier age. The teenagers make the best smokers, make the best soldiers. I mean, make the best, make the judgment a little differently. Okay. Light coming in, laser light coming in like this. Just look at the ray, and the laser light affords an excellent example of a ray. It bent. And that's what I wanted to see with the smoke. Hits the mirror, and how's this angle compared to this angle? Same, right? And when it comes out, does it continue like this? No. Why? It refracts. Let me ask you a question. Why does it refract and go in that direction? Why? Why does it refract to begin with? You got to know that. Check your neighbor. Okay, why the refraction, gang? Why does it refract anyway? What's light do when it goes from one medium to another? Changes speed. And when it changes speed, and if it's coming in at an angle, what's it going to do? Like those wheels, if one part changes speed and the other part doesn't, yeah? It's going to bend? So we see why light refracts. Get that? And so there's a change of speed from here to here. And like that, okay? So here we're refracting, reflecting, refracting. All in one little illustration. Question?
Wasn't there also a reflection off the water?
Did you see that?
Yeah.
Excellent, excellent. You saw the reflection off the water coming back down like that. Excellent.
Also saw one from when the beam
And up
came
here.
that way.
Up here.
And
Excellent, excellent. Here I'm concentrating on the part I want to teach about, huh? And you saw the whole show, honey. That's great, okay? There's a reflection here. It turns out water will also reflect light. You can't get any water that won't reflect a little bit. It's going to reflect some and refract some, okay? And coming down here at the mirror, reflect, some goes off here, huh? And some continued here. So you get all those. Very good. Lee?
What's the angle of the reflected light that just reflects before it goes down compared to the light reflected from the mirror? So the light reflected from the water and the light reflected
This
from the mirror.
angle here and this angle here would be the same
Yeah.
if this and this are parallel, okay? And this angle here would be the same as this angle here too, right?
No.
How many people say, yeah, okay, whatever you say, Hewitt. Come on, no, that's wrong. Okay, this angle here is smaller than this angle because we're refracting now, okay? And how about this angle here and this angle here? The law of reflection still holds. I want you to do something Saturday night when you take your bath. Saturday night when you take your weekly bath, get the tub all to yourself, all right? And take a flashlight, one of those waterproof jobs in the bathtub, and sit there and take that flashlight and shine it straight up. When you do it, you see a spot in the ceiling. Now take it and start turning it, turning it, turning it, and you turn it, turn it, turn it, and it turns out you'll get to a place, light will be coming like this, huh? And then go out like that, yeah? And you keep turning, you'll get to a particular angle where the light will all reflect, and none will come out. That particular angle is called the critical angle. And for water, that critical angle, I believe, is 48 degrees. 48 degrees. Less than 48 degrees, some goes out and some reflects. But beyond 48 degrees, gang, all that light will be totally internally reflected. And you know what makes use of that idea is light pipes, fiber optics. You're into those things. Fiber optics, with the bended little decorative lamps and whatnot, okay? Hey, fiber optics, it turns out that the hair on a polar bear, gang, the hair on the polar bear turns out to be a whole lot of fiber optics. And it has a preferential, it has a preference for ultraviolet. And ultraviolet is high energy, low energy. And polar bear want to get a lot of energy or don't care about the energy. Honey, if you're up in the Arctic, what do you want? A lot of, and you know what? It turns out the hairs on the polar bear's fur are light pipes and will guide the highest energy light right down to its skin. And the skin wants to absorb that light. Guess what the color of the skin is, gang? Black. So what's white and black and warm all under? A polar bear. Hey, physics, huh? Okay. You ever be wondering about a rainbow? Why you get all the colors in a rainbow? To understand a rainbow, first of all, you got to understand a prism. You know, if white light comes in a prism, you get different refractions. Different colors refract different amounts. It turns out you get red here, maybe, green here, and blue here, and sort of like that. And you guys know with a prism, you can get a nice spectrum. You call it a rainbow in the loose sense, yeah? But you get that in the sky, too. Why? Well, it turns out in the sky, rather than have prisms, you have little spherical drops. And those little spherical drops are like this. And what happens there? Sunlight coming in. The white light from the sun comes in, refracts, boom, makes one reflection, and then another refraction, and out here would come like red. Bam, some bends a little differently, comes out here. This would be maybe violet. And it turns out you've got an angle between here and here of, I think it's 40 degrees for the violet, and here, 42 degrees for the red. Early printings of the book have a mistake there. Okay. but at this sort of thing. So when you're looking at a rainbow in the sky, if you're standing down here and you look at raindrops up in here, and these raindrops are being illuminated by sunlight in back of you. Note, the sun is always in back of you when you see a rainbow, if you're facing the rainbow, yeah? And that sunlight comes down and back. Refraction occurs in the drop, reflection and refraction, yeah? And you're down here, and boom, you see the colors. Now here you are right here, if your eye is right here. For that particular drop, you see red. Okay? If you want to see the color violet, would you look up or down? Check your neighbor. Let's take a look, gang. If you got your eye down here and you're seeing red, to see violet, this one here, up or down, how many say you would look down? 1. Let's try that again. How many people say you would look down to see violet? 2. They're right. How many say you'd look down to see violet? How many are going to join the club? Come on. Study political science, get you all into that sort of thing. It turns out, gang, you would look down. Could I have a volunteer come up here? Julie. Yeah, Lee. 2 volunteers. Okay. Julie, you stand here. Lee, you get over here. Okay? Here, Lee. We want to answer the question, does everyone see the same rainbow or does everyone see their own rainbow? And why is the rainbow bow-shaped? Circle, okay? Turns out I took a flight in Kauai one time. On Kauai, helicopter flight. And the helicopter flight, the pilot says, if you look out to the side, you'll see the rainbows are completely round. And from up there, sure enough, they were complete circles. And then the pilot added, all rainbows are round. It's just that when you're down there, the ground cuts them off. So rainbows, gang, are completely round without the ground in the way. Let's see why they're round. Okay, Julie is the observer. Face the board, Julie.
Face the board.
Okay, now we're going to have sunlight coming right behind. Can you squat down just a little bit? Sunlight's coming right behind Julie. Okay, and that's right here. And there's a raindrop. And Julie, I want you to put your eye where the blue is. Okay, and hold that, please. Now, is there anywhere else that raindrops could come down and hit Julie's eye like there? Well, how about over here? No, there's no way. Over here, it's going to miss. Okay, so let's try this again. Julie, you hold that, and let's see where else, keeping this parallel. Oh, you can get it there too. You can get that one too, can't you? You can't get this one here, but she can get that one, can't she? And she can get this one, and she can get that one, she can get that. The criterion is that this angle remain constant for all those drops. And look at that. Julie can see all these ones. But Lee can't. When Lee looks over at this drop here, he gets no color. Thank you, Julie. Lee, you're standing over here. Stand right here. Okay? So you have to squat down a little bit, Lee, because this thing is a little high, okay? Okay, you look at the red, Lee. You look at the red, okay? Now you hold that, Lee. You hold it, okay? Lee can see a drop here. Can Lee see a drop way over there? No. Lee can see a drop here, here, here. Lee can see those drops. Lee, do you see the same rainbow that Julie did? No. Lee sees a different rainbow. So next time someone says, oh, look at that rainbow, say, what rainbow? Just kid with them, you know? You say, well, I'm not seeing the same rainbow you are. Is that true or false?
True.
That's right. Okay, Julie, stand like this. Lee, stand like this. Okay, closer, closer. Now look at the rainbow. Out this way. Are you guys looking at the same rainbow? No, different rainbows. A little closer. Same rainbow?
No.
Really close. Get down there, Lee. Same rainbow? But it looks better, doesn't it? Okay, thanks a lot, gang. Let's hear it for Lee and Julie, huh? Hey, all right. You've all done this. You've all gone scuba diving, or not, it's snorkeling at least, or just swimming in the water. How many people have not done this? Swim in the water at some time in your life. Go way down as far as you can. And then look up and see what it looks like. How many people have not done that? I want to see what you look like. Ah, we've all done that, right? And what have we seen? It depends on how rough the water is. What does a fish see when it looks up? Okay. The water, huh? Okay. The fish's point of view, looking up, is the same as the light coming down. See? Light coming from straight above comes straight down to the fish. Light coming like this bends like that to the fish. Light like this bends like that to the fish. And over here, maybe light like that just bends to the fish. And if the fish looks up this way here, the fish sees the bottom. So what the fish sees is a great, oh, the fish or you. You see a patch, you see a great big circle. If that water were perfectly clear, you'd see a nice circle. And the critical angle for water is 48 degrees, 48 in here. So what's 48 and 48? 96, I did it myself, okay? 96 degrees. So it turns out, if you're down there, you can see from horizon to horizon in a 96-degree view. See, when you're up on the top of the air, you got to go like this. Whoop, boom, 180 degrees. 180 degrees from horizon to horizon. But underneath there, only 96 degrees. That's why a fish wants to see horizon to horizon. Don't have to go. Fish doesn't have any neck. Doesn't need a neck. You just go like this. You go, okay? Do you see how that works? Okay. So in fact, what's a fisheye lens? A fisheye lens is just something that will compress a wide view into a and that's what sort of does here. So the whole view is up there. So you can look up here and see the sunrise, and look up here and see the sunset. Everything's in that conical view. Nice big circle at the top. Next time you go swimming, watch for that again. Watch for that. You'll see little splots where you can see out. That's where the waters are a little bit tipped. But perfectly smooth, you'd see a nice circle, and you'd see a cone. You come over here, of course, the circle would move with you, wouldn't it? Hey, wow, look at the circle. How does the circle know? Because you're special, that's how. Okay, you get the idea. Here's another thing, too. People who are nearsighted, underneath the water, can see very nicely. Yeah. I wonder if there's a reason for that. No, there's probably no reason for that. Think about that. The way the light bends going from water to eye is different than from air to eye. Less change in speed, less bending. Maybe that would have an effect. What do you suppose? I got a homework assignment for you guys. I got a homework assignment. That's the granddaddy homework assignment, okay? Let me tell you what it is. You see that door? Let's suppose that whole door is a mirror. Pretend it's a mirror. If I stand one body length away, could I see my whole image in that mirror? How many say, no, the mirror would have to be bigger than that? You do it. Stand up. Nobody, right? We know you can see yourself in that whole, okay. How about if I made the mirror smaller? Could I see myself? Could I see myself if I made the mirror like this big? Exactly the size of my body, right here, huh? And I get over here. Would the mirror be big enough to see all of myself? How many say, no, it has to be bigger than you? Who said that? That'll be big enough, yeah? Could I make the mirror smaller still? Could I stand one body length away and see myself, full image, in a mirror smaller than my height? To make the numbers easy, let's suppose I'm 6 feet. Not quite, huh? 6 feet. Could I make my mirror like 3 feet? 4 feet? 2 feet? 1 foot? Tiny, tiny? How big would the mirror have to be? And guess who's going to do that for homework? You. And you know what? You can stand in front of a mirror at home. You don't have a full-length mirror? Stand in front of a face mirror. Stand in front of a mirror like this. And here's what I want you to do. Stand in front of the mirror. Mark where you see the top of your head. All right? Now mark where you see the bottom of your chin. Don't move now. Now mark where you see the bottom of your chin. Measure the distance between those two marks. Compare it to the distance between your face. If it's the same, then you give me an answer that says same. But it won't be the same. Or will it? Do it and find out. So how big the mirror got to be compared to your height to see you? That's question number 1. Question number 2 is this. Okay, you find out what size the mirror got to be. You can have a friend help you by standing in front of a full mirror and putting a little piece of tape or lipstick or something like that and put some marks. You know, you see the top of your head, the bottom of your feet, yeah? Now, what effect does distance have on your answer? If you step back further and further and further, what happens? Can you still see yourself in that mirror? Or can you see yourself in a smaller mirror? Or do the mirror have to be bigger? The answer to that question is very surprising to a lot of people. What effect does distance have on your previous answer? Check that out. Try it. You're going to see something that perhaps has escaped your notice all your life. Now, when's the last time you guys looked in a mirror? Last week, something like that, yeah? And you probably won't look in the mirror for another few days, yeah? Okay, with this assignment, you look in the mirror today. And when you look in the mirror, look for the physics in the mirror, huh? Come on, you guys look in the mirror all the time, ain't that true? Look at the physics in there, too. Next time, yay.
Are the questions on the back of the book?